Hello everyone, and welcome to today's presentation. I'm excited to have you here as we discuss HVAC air balancing and field verification. On this first slide, we'll be focusing on the key steps involved in ensuring your HVAC system is balanced and verified properly. We'll cover how to identify VDs, verify diffuser CFM, inspect flexible ductwork, and match design readings. Over the next few slides, I'll walk you through each of these important processes to help optimize your system's performance. Let's get started. Today, I want to talk about the HoldPeak HP-866B vane anemometer. When using this device, it's best to operate it in AVG mode, which helps provide a stable average reading. Make sure to keep the vane perpendicular to the airflow. This orientation ensures accurate measurements. It's also a good idea to take multiple readings rather than relying on just one, as this improves overall accuracy and gives a more reliable picture of the airflow conditions. These key points are essential for obtaining precise and consistent data, which ultimately supports our broader goal of ensuring effective airflow management and measurement. Let's walk through the key steps for measuring air velocity accurately. First, make sure to set your measurement units to meters per second, or ms, to keep everything consistent. Next, I recommend using the AVG mode on your instrument. This helps stabilize your readings, especially if there are fluctuations. When taking measurements, aim for about 5 to 9 points across the face of the diffuser. This gives you a more representative reading of the entire airflow. It's also important to keep the vane centered and flush against the surface to ensure precision. Lastly, avoid any external drafts or obstructions that could interfere with your readings, as these can lead to inaccurate results. Following these steps will help you get reliable, consistent air velocity measurements that support the overall accuracy of your system assessments. Let's take a closer look at the CFM conversion formula. This formula helps us calculate the airflow in cubic feet per minute, which is essential for understanding ventilation efficiency. The formula is CFM equals V times a K times 2119. Now, V represents the measured air velocity in meters per second, so it's the speed at which air is moving. The K stands for the cross-sectional area of the neck, and we estimate that as between 0.6 to 0.7 times the neck area. What's important here is how these components come together. The velocity tells us how fast the air is flowing, and the area indicates the size of the opening through which the air passes. Multiplying these gives us an idea of the volume flow rate, and the factor 2119 is a conversion constant to get our units right into cubic feet per minute. Connecting this to our overall theme, understanding this formula allows us to accurately measure and control airflow, which is crucial for maintaining safe and effective ventilation systems. Now, let's take a look at an example calculation for a 400 by 400 millimeter diffuser. The key measurements here are the neck area, which is 0.16 square meters, and the K, or the cross-sectional area, which is 0.112 square meters. When we consider airflow velocities, at 2.9 meters per second, we're looking at approximately 688 CFM, or cubic feet per minute. If we reduce the velocity slightly to 2.6 meters per second, the airflow drops to around 616 CFM. What this illustrates is how changes in velocity directly impact airflow rates through the diffuser. This is important because it helps us understand how to size and select diffusers based on the airflow requirements of a space. Ultimately, this example underscores the importance of precise calculations in ensuring effective and efficient ventilation, which ties back to our overall goal of optimizing air distribution in our systems. Let's walk through a quick example calculation for a 300 by 300 millimeter diffuser. First, note that the neck area is 0.09 square meters, and the actual opening area, a K, is 0.063 square meters. When we set the velocity at 2.9 meters per second, we get an airflow rate of about 387 CFM. If we reduce the velocity slightly to 2.6 meters per second, the airflow drops to approximately 347 CFM. The key takeaway here is how the velocity directly influences the airflow volume. slight adjustments in speed can make a noticeable difference in performance. This example highlights the importance of understanding these calculations to optimize diffuser design and ensure proper airflow distribution in the overall system. Remember, balancing these parameters is crucial for achieving the desired comfort and efficiency. Let's take a closer look at how we convert between metric and imperial units. For example, 1 meter per second equals 197 feet per minute. This conversion factor helps us translate velocities measured in metric units into the imperial system. Now, when it comes to calculating airflow, we often use cubic feet per minute, or CFM. The key formula here is that CFM equals velocity in feet per minute multiplied by the cross-sectional area in square feet. Understanding this relationship is crucial because it allows us to accurately size and evaluate ventilation systems, regardless of whether we're working in metric or imperial units. So, by mastering these conversions, we ensure that our calculations are consistent and reliable, which ties back to our overall goal of designing efficient and effective airflow solutions. Let's go through the checklist for low CFM zones. First, ensure that the VD is fully open. This is crucial because a partially closed damper can restrict airflow, impacting system efficiency. Next, check that the diffuser is clean. A clean diffuser helps maintain proper airflow and prevents dust buildup, which can affect air quality. Then, verify that there are no flex kinks in the ducts. Kinks can significantly reduce airflow, so straight, unobstructed ducts are key. Also, make sure the filter and coil are clean. Dirty filters and coils decrease system performance and energy efficiency, so regular cleaning is essential. Don't forget to confirm that the fan is rotating correctly. Proper fan rotation ensures the system operates smoothly and delivers the right amount of airflow. Lastly, check for any duct leaks. Leaks can lead to loss of conditioned air, reducing comfort and increasing energy costs. By systematically going through these points, we ensure the zone operates optimally and maintains the overall system efficiency. Now, for balancing the target and achieving the desired design airflow, the key is to adjust all the VDs, or volume dampers, so that the measured CFM, or cubic feet per minute, is within about plus or minus 10% of the original design specifications. This ensures that the airflow is neither too high nor too low, maintaining optimal system performance. If you find that all the readings are consistently low, that's a good sign you might need to check the cleanliness of the system, filters, coils, and ductwork, and also consider slightly increasing the fan speed. Small adjustments like these can make a significant difference in reaching the target airflow and ensuring the system operates efficiently. Remember, the goal here is to fine-tune the airflow so it aligns with the design intent, which supports the overall efficiency and comfort of the system. Consistent monitoring and careful adjustments are key to achieving that balance.